Hello students, we'll be trying to solve another problem today. So in this video, we'll be attempting to solve 2019 May problem, which was asked in KTU. So this problem was asked for 12 marks, and it is from module 5, and in module 5 it is from the stress transformation area. So the question is, at a point in a strained material, the direct tensile stress of 70 Newton per mm square, 70 MPa, and a direct compressive stress of 50 Newton per mm square are acting on planes at right angles at each other. If the maximum principal stress is limited to 75 MPa tensile, determine the shear stress that is allowed on these planes. Also determine minimum principal stress, maximum shear stress, and direction of the principal planes. Okay, so this is not a very direct question, but if you know all the formulas, you can easily solve this. So what I will do, I will draw the stress block first. So I'll assume this is x direction, this is y direction. Let's say in x direction we have the first stress of 70 MPa, which is tensile. Okay, and compressive stress of 50 MPa in the perpendicular right angle. Okay, so this is compressive stress here. So that is 50 MPa. Okay, and there is some shear stress in this plane. Shear stress is we don't know the shear stress. So we will draw the shear stresses. So we'll call the shear stresses tau xy. Okay, shear stress is unknown. We have to find the shear stress. Okay, so that is the first part of the problem. Now sigma x is plus 70 because tensile is assumed to be positive. Sigma y is minus 50 because it is compressive, and shear is tau xy. Okay, now the condition that is given is the maximum principal stress is limited to 75 Newton per mm square tensile. Okay, so principal stress formula is given by, if you recollect, it is sigma x plus sigma y by 2 plus minus under root sigma x minus sigma y by 2 square plus tau xy square. Okay, so we have two principal stresses, plus and minus, one with plus, one with minus. So this value, the maximum value, is limited to 75. So it is a straightforward question. This sigma 1 cannot be more than 75 MPa. Okay, so if you incorporate that condition here, let's say we will take plus, this will be positive, this also seems to be positive, so plus plus plus, you get a positive fold stress, that means a tensile stress. So maximum tensile stress is when we consider the plus here. Okay, so it is limited to 75, so it is equal to sigma x plus sigma y, so 70 minus 50 by 2 plus under root of 70 plus 50, because it is minus minus will become plus, by 2 plus tau xy square. Okay, so only unknown is tau xy. We can directly solve this to find the value of tau xy. So this gives me 70 minus 50 is 20 by 2 is 10. 75 minus 10 is 65, equal to 70 plus 50, 120 by 2 is 60, so 60 square plus tau xy square under root. Okay, so tau xy is nothing but, tau xy square is nothing but 65 square minus 60 square. Okay, so tau xy is under root of 65 square minus 60 square. This comes out to be 625 tau xy square. Okay, so that means tau xy is 25 MPa. So this is the first part. The shear stress here should be 25 MPa, so that the maximum principal stress is 75 MPa. So that is done. Now they are asking what is the minimum principal stress. So minimum principal stress is nothing but sigma 2. So is sigma 2 is equal to sigma x plus sigma y by 2 minus under root sigma x minus sigma y by 2 whole square plus tau xy square. Okay, so this is one way of finding it. So there is another easier way. The another easier way is if you know a small identity. Small identity is irrespective of the orientation, the sum of the normal stresses in a stress block at a point will be always constant. So that means what I am trying to tell is sigma 1 plus sigma 2 should be equal to sigma x plus sigma y. Okay, any of these two you can use. Either you can use these two. We know the value of shear is 25. We know sigma is sigma y, so you can calculate this. Or you can use this identity, sigma 1 plus sigma 2 is sigma x plus sigma y. Okay, so sigma 1 we know it is nothing but 75 plus sigma 2 equal to sigma x is known 70, sigma y is minus 50, so it is 20. So sigma 2 is this 20 minus 75, which comes out to be minus 55 MPa. Minus 55 MPa. So if you do this also, you will get minus 55 MPa. Okay. So this is a smarter way of doing it, very faster way. Instead of calculating all this, it is very fast to calculate a small addition subtraction problem. Okay. So this is there. So this part is done. So we have done shear stress is done. We have found the minimum principal stress. Maximum shear stress. They're asking maximum shear stress. The value of maximum shear stress is given by this expression. This will give the maximum shear stress. This is also the radius of the Mohr circle. This expression will give the radius of the Mohr circle also. Okay. So tau max is given by. So I think I will continue here. So I'll give a separator here. So let's say tau max is given by under root sigma x minus sigma y by 2 whole square plus tau xy whole square. So this is nothing but under root of sigma x minus sigma y by 2. We know it is 60 square plus 25 square. So this comes out to be something around. So we can calculate this, or we can observe here 60 square plus tau xy is 25, 25 square is 65. That is also there. Okay. So this shear stress is there. So this is done. Shear stress, maximum shear stress is there. Direction of principal plane is there. Okay, direction of principal plane we have to use the last identity, tan of 2 theta p equal to this by this. Okay, without any. Okay, here I am sorry. Here I have missed the square sign. So please check that. I have done the calculation correctly. Yes, missed the square sign here. Okay. So tan 2 theta p is nothing but shear upon sigma x minus sigma y by 2. Okay, so this term by this term without the squares. So this comes out to be something around 25 by 60. This is 25. Sigma x minus sigma y by 2. It is 60. And this gives me 2 theta p equal to tan inverse of 25 by 60. Which comes out to be 22.6 degree. So principal plane is nothing but theta p equal to 22.6 by 2, that is 11.3 degrees. So this is the principal plane. So we have answered this question. Now to complete this, to complete our understanding, we will draw a diagram and finish off the problem. So always drawing the diagram, it is very fast. I will recommend you to draw the diagram always whenever you are able to manage the time. Okay. So this shear value we have already found. So I'll just write the value here. So this is 25 MPa. Okay. Now this, if I rotate this, make a copy of this. I'll rotate this. This angle of rotation is nothing but 11.3 degree. Okay, this is the angle of rotation. So when we do this, we get the principal plane and the values for principal stress is sigma 1 and sigma 2, which is given by, this is 75, which is already given to us, and this is 55, which is, we found that. Okay, it is compressive, this is tensile. There will be no shear because it is a principal planes. Okay, so I hope this is clear. This concludes our answer. I think we can meet each other in another video with another problem. Thank you.